If you observe the Amazon rainforest, its sheer volume of vegetation suggests an incredibly rich foundation. But tropical soils are typically sandy, highly acidic, and nutrient-poor. Constant, heavy rainfall aggressively washes away fresh organic matter before it can accumulate. Yet interspersed within this basin are pockets of what we call terra preta, or dark earth. These localized patches are highly fertile and dense with organic matter. They exist because thousands of years ago, ancient human populations deliberately worked large amounts of black carbon into the dirt. Today, we refer to this black carbon as biochar. Physically and chemically, biochar is charcoal. It is the same charred material humans have produced for thousands of years. The distinction is one of purity and purpose. While commercial charcoal often includes additives like paraffin to help it ignite for fuel, biochar is kept in its pure form, manufactured exclusively for agricultural integration, not for fire. It does not act as a traditional fertilizer, meaning it does not feed plants directly. Instead, adding biochar creates a structural matrix that alters the physical and chemical architecture of the soil over millennia-scale timelines. To manufacture this material, raw organic waste undergoes pyrolysis, the thermal decomposition of biomass inside a rigorously oxygen-deprived environment. In an open fire, unrestricted oxygen allows the biomass to fully combust. The organic material is reduced to fragile ash, and its stored carbon is released into the atmosphere as carbon dioxide. A two-chamber reactor separates the heat from the oxygen. The outer chamber heats the system, while the inner chamber blocks oxygen. Intense heat degrades the wood structure, cleaving linear carbon chains. Liberated carbon atoms restabilize into interlocking hexagonal rings, forming a highly stable aromatic matrix. The final matrix's architecture is dictated by the specific temperature curve inside the reactor and the type of biological waste you start with. Higher temperatures generally yield a carbon structure with a larger surface area and a higher degree of physical porosity. This requires a deliberate thermodynamic trade-off. We give up the high energy yield we would extract from fully burning the wood. In exchange, we manufacture a recalcitrant carbon scaffold capable of lasting thousands of years. When this charred material is moved out of the reactor and tilled directly into a live agricultural field, its unique physical properties take effect. If you amend a field with standard organic compost, you are introducing loose carbon chains that soil microbes can easily digest. In a hot, arid climate, those microbes rapidly mineralize the compost, consuming it entirely and releasing the carbon as CO2 within a few years. Compost degrades rapidly as microbes consume it. But biochar's aromatic rings resist digestion, maintaining a flat retention curve for a millennium. This longevity provides extreme cation exchange capacity. Microscopically, positively charged nutrients are magnetically attracted to negatively charged biochar pores, locking securely in place. Simultaneously, the physical void spaces within the biochar provide necessary structural shelter. Beneficial microbial colonies and mycorrhizal fungi establish themselves deep inside these microscopic cavities, protected from predators and environmental stress. Applying biochar shifts the strict logic of soil management. Instead of constantly replenishing dirt with fast-decaying nutrients, you upgrade the soil's permanent physical capacity to hold on to whatever nutrients are introduced. However, the intense thermal processing of pyrolysis creates a strict agronomic constraint. As the biomass burns, acids are driven off, and base cations are concentrated, leaving the resulting biochar highly alkaline. In an arid region like Oman, native agricultural soils sit at a high pH. Adding an alkaline amendment risks pushing the pH to toxic levels. To buffer alkalinity, elemental sulfur is added. It oxidizes into sulfate, releasing positive hydrogen ions that acidify and neutralize the biochar. But there is a secondary risk. The empty porous matrix acts as an aggressive nutrient sink, immediately immobilizing ambient phosphorus and starving the crop roots. To prevent immobilization, raw biochar is incubated. By mixing it into an active compost pile before field application, the empty pores are preloaded with nutrients. Biochar is not a universal plug-and-play additive. Its success depends entirely on precisely calibrating its chemical profile to match the specific pH and nutrient deficiencies of the host environment. The biochar life cycle is a dual utility system. It processes agricultural waste while operating as a carbon sequestration tool. The flowchart maps the quantitative advantage. Pyrolysis successfully retains up to 50% of initial carbon, locking it strictly in a stable state. If that exact same biological material is left to rot in a municipal landfill or is processed through an industrial incinerator, 99% of its carbon immediately returns to the atmosphere as greenhouse gas emissions. Scaling this technology effectively relies on high-volume manufacturing as well as precise, localized chemical buffering to ensure the host soil safely integrates the amendment. By solving the chemical constraints of specific environments, we move past treating agricultural soil as a consumable resource that requires endless feeding. We gain the ability to engineer the earth itself, building millennium-scale infrastructure directly beneath our feet.